Right. So today we are continuing playing around with this little expression language. So I'm going to do a recap by scrolling down the screen. So we started with untyped expressions. And then we saw that in order to evaluate these, we could only maybe produce a value because not all expressions made sense. Right. But then we switched to type expressions. We say that type is either num or bit. And then gloriously, when we evaluate these things, we could always produce a value. And also the evaluation function somehow got easier, right? So we paid up front by actually classifying things with types. And then we got paid back by having an easier job eventually.
Because most languages wouldn't have, like if you're talking like Lisp, you just get errors rather than maybes.
Right, you get a runtime error, yes, yeah. Yeah, I mean, that's of course another thing you could do. So here we said that values are either numbers or bits, but you could also throw in a "I'm going to crash now" value, right?
Which would be equivalent to a maybe.
Yeah.
Yeah, but it's at runtime, so you wouldn't so easily see.
But you'll sort of, the errors will happen at the same place.
So today, I thought we'd start by trying to make sense of there's some relationship between the typed and the untyped expressions. And then hopefully we'll also have time to optimize expressions. So there's kind of one direction that's very easy here, right? If you have a typed expression, then you can forget about the type, and that gives you an untyped expression. If you have more information, you can get less information. So yeah, so here I'm just saying, given any typed expression for any type t, I can produce an untyped expression. And this is going to be a very boring function. So I'm going to pattern match on E, see that these are expressions I have. And then I'm just going to return the same thing, but in the untyped variant, right? So here I can say, do the customary renaming first.
Yes. So it's kind of funny that there's something terribly important that we said to you that we didn't tell the computer, which is that the typed expressions are the typed version of the expressions.
This is what you're saying.
As far as AGDA is concerned, we just invented a whole other data type whose connection with the one we first thought of is not at all apparent. And this is a bit of a pity, because if we had been able to say, this is the typed version of the expressions, then we'd have got this function for nothing.
Yeah. Is there a way to say that? I'll try to
so if you know what you're doing, there's a way to do that. But it's maybe later.
Yeah. So for now, let's just do it the stupid way by doing it ourselves, right? So it's not really about adjoints at this point. It's more about okay. Let's do that later. Yeah. Okay. So I'm going to say that the typed num I map to the untyped num, the typed bit I map to the untyped bit. And then if I have a plus, I want to map this to an untyped plus, where I just continue erasing E and E prime. And here's a stupid technical thing. I probably shouldn't have used these bars for erasure, but it looks nice. But you can't just type a bar because that's the with bar, right? So this is really a backslash bar, just to make Connor happy.
Well, it could be worse. It could be a special Unicode space.
Right. Yeah. Okay. And then if I have an if then else, I'm going to raise this to an if then else. Where again, I'm just keep erasing all the sub expressions, right?
So the only reason you need to pattern match is so that you can do this sub expression, recursion sub expressions.
Yeah.
Yes and no. I mean, the pattern matching is really important because otherwise I don't know how to erase it, right? Because it looks like it's the same thing on both sides, but they are really different things with the same name.
Even though it's not the same thing. Okay.
So
It's
it's,
fair to say name is enough for it to realize.
yeah, it wouldn't make sense to say the erasure of X is X,
Even if you don't have the E in.
even if there was nothing, if I only had num and bit.
Yeah.
Right, because this just doesn't type check. This X here is
It's
still.
just- yeah, okay,
Yeah. So it is
So
one of
you
those.
really do need to go through it.
Constructors have the same name.
Yeah.
not the same constructor.
It's more of a coincidence that the constructors have the same name. Okay, so it's very easy to go this way, right? You start with more information, you get less information. But you could also imagine that sometimes you can go the other way, right? So let's declare a record that tells us what it means to go the other way. So here I'm saying I have an untyped expression, E, and this is the data that you need to provide in order to say that this really is a well-typed expression, right? So saying that E is well-typed if there is some type, which I call tau, which is maybe also not a great name, and there is some expression T, which is a typed expression, such that if you erase it, you get the original E, right? You're saying that E is well-typed if there is a typed version of it somewhere, such that you can go back again. Yeah. So now we could hope to go the other way and say that given an expression, we could hope to find a proof that it actually is a well-typed expression, right? But we know that not all expressions are well-typed. We can do false plus 7. That's not going to be well-typed. So we, again, can't hope to get a proof that every expression is well-typed. We can only get a maybe proof here, right? And I call this infer because we're in some sense doing type inference, right? We're trying to figure out what this type is here that makes it work. And
So you implicitly use the fact that there'll be a unique T.
well, it's up to me to find the T, right? So when I write this infer function, then I get to choose it. There is only going to be a unique one, but it wouldn't a priori be a problem if there was more than one, right? And in the coursework, I've asked you to do the other thing where you, instead of trying to find out what the type is, you're given a type up front, and then you need to check if the given expression you've been given actually matches this type or not, right? Which again is not always going to work, right? Right. Do you want to do this, Connor, or should we?
I could give it a go. Let's see what happens. I wonder, actually, can you start while I just find my other spectacles?
Okay. What do you want to do first? I think you want to pattern match on the E.
There's one game in time, and that's the pattern match on E.
And then I think you would like to rename these things.
Yes.
Oh,
That's what happens to the whole issue there.
okay, so now we can really start.
I've reached the stage of my life where when someone says, shall I pass you the menu? I say, no, but could you please hold it slightly further away? Okay, so now, interesting questions include what style I should adopt with records here.
I've given you a constructor, so I think you should use the constructor.
Okay. So, okay, we've got a number. Do we think it's well typed? Yeah, it's going to be well typed. So I say, let's
say just okay.
Okay, I've got to say just. Refine is happy. Okay, so what I'd love to say for goal 7 straight away is REFL, but I think, well, anytime I'm saying okay, systematically, I'm going to say it's we deliberately made the typed expressions look just like the expressions. So I'm going to give the expression, and then I'm going to say solve constraints, because I'm not going to ask you what the type is or guess myself when I can tell Agda to figure it out.
What's the thing for solve?
Control C, Control S.
Oh, solve. Right.
S for solve. Yeah.
And now our equation is reassuringly,
If you put REFL in 7 to start with, you'll be able to solve the constraints.
it wouldn't, it's not going to be clever enough to run the erasure function backwards.
Okay.
That's one thing that, one game that Agda won't play is inverting functions. It'll invert constructors, but not functions. Okay, bit B, same story, right? Okay, we say bit B here, and then we do solve constraints, and that's, oh yeah, my finger's doing stupid things. Okay. So far, so good. Now, what do I want to do here? I expect
I'd recommend a do block.
a do block is probably the right thing. But I might need some help with the funny pattern matching. Let's see
I
what
would
happens.
recommend to do the do block outside of the goal. because-
Yes, okay.
Is the reason you can do a do block because you've got the baby wrote out.
Yeah,
Right, because maybe it's a monad and bind for maybe it's in scope. So the do block makes sense.
right. So what's gonna happen is I'm gonna get myself T comes from infer E, and T prime comes from infer E prime. And unfortunately, that much is nice, but I can't. What I would really like to do now is case split on T and T prime.
Yeah, which you can do. You just have to do it manually.
Yes, that's what I meant. What I want the machine to do is case split on T and T prime. Okay, so I'm going to look. If I'm lucky, I've got okay. Right. So crucially, I don't just want. I'm quite biased as to which type I want.
I mean, you could do it in slightly smaller steps, right? There's no luck involved to say that this is going to be an okay for some type and some term and some proof, right?
Yes. So I'm going to call this. I'm not going to try and type it out.
No, that's fine. So that's some T prime.
T prime and Q prime. Okay. So let's just have a look at what we've got. So we've got some handy facts. One thing I can see is I've got a pair of equations which have a variable on one side. So I have no compunction whatsoever.
Is this Q and Q prime?
Q and Q prime, they're both equations and they have a variable on the right-hand side.
Right.
So I just want those equations substituted. So I instead refine my pattern variable Q to the constructor REFL. And now we'll see what we are after. Now we want maybe well-typed erasure of T plus erasure of T prime.
So this used to say E and this used to say E prime, right? Before we pattern matched on the REFL, which said that they were really equal.
Okay. So now I'm hoping I can learn to do the where trick.
Yeah.
Because I know I've got a particular prejudice about which T and which T prime I want, right? It's not okay for T and T prime to be well typed, for either T or T prime to be well typed bits. So I'm going to see if I can get this right. I say num here.
Yeah.
And then I say where, and do I just say underscore goes to nothing? Would that do it?
Yeah, except it's a lowercase n in nothing.
Okay. So let's see. Do things one at a time. Check carefully. Okay, so you can see little t is definitely numeric.
Down here, right?
Yep. So same again.
Oh, big T's not there anymore because we don't have a variable called big T.
Yeah.
No, because we pattern matched on it.
Okay. So this is looking pretty good. In fact,
Yeah.
what happens if I do that? No, that's too obvious.
Well, failure is always an option, right?
True. Can you find anything else? Oh, goodness me.
This solution.
Yes.
That's good.
Yes. So so Control C, Control A is like hitting the I feel lucky button on Google. But you have other options. So I type -L into my hole, and I do the same thing, Control C, Control A, and that gives me the top 10 hits. There's only 2 hits here. Funny that, isn't it amazing that because the program is actually a really decent, the type of the program is a decent specification. There's no chaff here, right? These are the 2 things which type check.
So if you put 1 in and then control A, that would be
Right. Yeah. So then what I say is -S1, which means skip 1. And we are laughing. It's okay. There was a bit of I had to do some barking myself, but when it came to the final act,
So
the dog figured it out.
the where underscore goes to nothing.
Yeah. So
Happening.
So here we did a particular pattern match, right?
Yeah.
So we pattern matched on OK, and that was no big deal because we had a record. So every element of the record is an OK of something.
So you did none, you're saying
But-
everything else goes to nothing.
Yeah, but then and similarly when we did pattern match on REFL, that's also no big deal because that's the only constructor. But when we did num, that's not the only case, right? There are other cases, and we're saying for all the other cases, we're going to return nothing.
yeah. So this is a particular thing that it has been added to make do blocks
Nice.
friendlier when there's only one pattern that you want and everything else is a failure. So you just have a way to sort of take the failure case off to one side and explain how to go wrong as gracefully as possible.
I mean, you don't have to put an underscore here, right? You could put an X and then you can put an F of X here and deal with all the other cases. But most of the time we kind of have a happy case and then everything else we just return nothing.
Okay, so let's play the same game, except that I will have to think a little bit harder at some point.
Yeah, maybe even make something up.
So we're going to do some bits and pieces. Okay, let's get the easy bit. The one thing is going to be, I'm going to call this OK bit B REFL comes from infer E where underscore goes to nothing. Right.
Because this is the same as before, right? We're only happy if the condition really is a bit.
Yes.
Otherwise, we have no choice but to return nothing.
So right angle language isn't calculating some expressions. So that E were doesn't matter, there's some expressions given bit.
It has typed bit. It's not lowercase bit, right? It could be a complicated thing.
It could be kind of if then
An
else.
if.
a bit,
Yeah, that's part of missing. Okay.
Yeah.
Okay. Now, what happens next is, well, that I can get back some stuff from these things. Okay, but I'm less convinced about whether or not I want the that I know exactly what type I want.
As we said in the FTNLs that we can have any type of the two branches as long as it's the same type, right?
Yep. So at the moment, if I ask for this list of solutions, I'm only getting failure because it's not yet obvious that, although my then branch and my else branch are well typed, they're not obviously the same type. So I've got more work to do. I'm going to need to test whether T and F are equal. And if they are equal, I will want the evidence that they're equal, right? So just getting true or false won't help. And in the case where they are equal, I actually need something that enables me to substitute one for the other.
Like capital T or
capital T and capital F. Yeah. So I'm going to need, I don't know what to call this. I'm going to call it type. Is that a reasonable name? Yeah. Which takes S and T of type tie and gives me maybe a proof. What is this?
Backslash
equals. Maybe a proof that S equals T.
So if you put on the bottom line, okay, TF, that wouldn't work.
So where?
That capital F, the going capital T.
Yeah, if I say that, then all I do is I introduce a fresh pattern variable called capital T, which inconveniently shadows the other one.
So it's got the reference to say why this can make it.
All right. And in general, you're not going to get equality testing just by casually repeating variables. You have to do a computation to figure out whether two things are equal.
It's the same if you say lambda x and then you say lambda x again, right? That doesn't force the two x's to be the same. It just means you shadow the first one.
So I'm going to say Q comes from tie ecat TF. Sorry, that's a
Looks good.
the American pronunciation of the question mark at the end of the name, as opposed to if you're Canadian, you say tie gay, or if you're Australian. Okay, so what's just happened? I'm checking that it's fit for purpose before I bother to implement it. Yeah. So if I'm lucky, I get a proof that T equals F.
Still Q here, right?
Right. And now I do the usual thing. I refine that to REFL. It's the only choice. And now I can see that if I scroll down a little, I now have two typed expressions with the same type. Thank goodness for that. So let's now do -L, Control-C, Control-A, and hooray! It's now figuring out the answer for me. I've got enough information now that there is a proper solution. So if I do that, we're done.
See where everything else goes to nothing for all the other cases.
No,
So-
because these binds here are saying if this thing returns a just, then continue. If this thing returns a just, then continue. If this thing returns a just, then continue. If any of these are nothing, then the bind
Yes.
will return nothing.
Checking for just is built into the maybe monad and is given to me by the do block. I need
Check for anything else.
failure cases when I'm matching on particular types, because then there's the possibility that it's the other type. So this where underscore goes to nothing is dealing with the case where it's well typed but a number. And the earlier ones were dealing with the case where E and E prime were well typed but bits. Okay, so all I have to do is finish this job. And what do? I look at both S and T. And then I remove the off-diagonal cases in favor of a catch-all. And then I say just refl, just refl.
I assume we could have solved that one itself.
Well, it could have, it would have said you can have just refl or nothing. I mean, nothing was still an option.
If you didn't ask for more solutions, it would have returned nothing because
Okay.
that's the easiest way to do it. Right?
So we're there. We had to build ourselves something that would get evidence of type equality. We had to do some inspection of types which came back to see whether they were the types we wanted. But at the end of the day, we produced something which is sound by construction. That's to say, if this program succeeds, you definitely get a well-typed term, not just any old well-typed term. It's the well-typed version of the term you first thought of.
We'll say if you do infer, then the other function you're ready to find, you get back to where you started with adjust.
Yeah, because that's what the is same is telling us, is that success means, we've if we didn't have is same here, then we could just ignore the expression that came in and give back our favorite well-typed term. We could just say, congratulations, here's num37. Whereas this way, at least we get a guarantee that whenever the computer says yes, it's saying yes to the question we asked. So yeah, there are fun things. We aren't yet being all that clever about completeness. We are free to say nothing for things which actually do have well-typed versions. So, but we are at least guaranteeing soundness.
So you say you could have defined infer just means up on everything.
Yes. Yeah. So we can play similar games to what we did for typed terms. You can actually consider how to write down a data type that represents a term with a leftmost type error or something like that. You can actually, so we wrote down what the well-typed terms were. You can also write down a representation of types which definitely, or terms which definitely contain a type error. And then instead of just saying that you either get a well-typed term or nothing, you can say you either get a well-typed term or a proper error diagnostic that points out the type error in the term you first thought of. But and it's essentially the same technique as we used for the positive option,
Right,
to collect the evidence.
it would basically just mean that all of it going to nothing here would
Yes,
go
you
to
would
something
actually
more
point out something more interesting, that.
Okay, so we have a little bit more time, so let's.
Would that second thing be going to a maybe, or would it be going to
It would,
well-typed or not well-typed?
the second, right? I mean, maybe is
If that's
well-typed
all-
or one more
Yeah.
boring thing, right? So we're just replacing that boring thing with something actually informative in that case.
Yes. This program is old enough to buy drink. I'm just thinking, how old is this program? It's 18. Actually, it's older than that. It's about 20.
Okay, so if we have these expressions, because they are a data type, we can actually match on them and do interesting things with them, right? So one thing we could want to do is could maybe replace one expression with a more efficient version of the same thing. And what I mean with the same thing, I mean that they should evaluate to the same thing, right? So here, just as a silly example, I would like to write a function that takes an expression, and whenever I have an if false or an if true, I'm just going to reduce that to the branch it should actually be, right? Just as an example. So let's see how we do it. There's some, it sounds easy, but there's some small pitfalls. And the fun thing, of course, is that we can now actually prove that it does the right thing afterwards. But this time I'm going to just write down a function, and then afterwards I'm going to try to squeeze the tooth back in the tube and prove that it did the right thing. Whereas here we were a little bit more proactive and said, okay, we're only going to produce well-typed things by design, right? Okay, so what does it mean to reduce these ifs? I'll do the renaming, because why not? Well, we have to look at all of these different things, and the if case
I think
is,
you want those to be ET.
yes.
Okay.
The if case is the interesting one, right? But we have to deal with all the other cases. For nums and bits, there's really nothing to do. So I'm just going to return. You basically just have to write it out, because who knows what.
Identity for everything but if.
Yeah. Well, you.
Okay, so I could do these two cases. I could leave as a catch-all at the very end, right?
yeah.
But when I get to the plus here, I really want to traverse the subterms and also do it. So I just don't do it for the top level, right? So here I want to do a reduce if e plus reduce if e prime, right? So you could write this as a fold, etc., but I don't think it really buys you much.
Yeah.
Okay, so these cases, I'm just going to leave them alone. And in the if case, well, here it's really tempting to look at the e and see if it's a bit, in which case we should reduce it, right? But that's a missed opportunity, because what if this e were to be a bit if only we did the same optimization to it first, right? So I'll try to remember to say, I'll try to reduce it. And then I can look if it's a bit or not.
We know it's a bit already, right? If this is the typed expression.
It's type bit, but it might not. I mean, after I reduce it, it is definitely going to be a bit, in fact. But before I reduced it, it could be another if, for example, right?
Oh, so the output's a bit.
Yeah.
Yeah. Okay.
So now here, okay, so here I get two choices. It could either be a bit, or maybe it could be an if then else. If we actually had variables, then it could definitely be an if then else, right? But so then here I can look at the x. If it's false, then I would like to return, yes, sorry, doing the other way around, because if it's true, I would like to return just this branch, right? But I might as well optimize this as well. I mean, it would be stupid not to. So I'm going to return reduce if of et in this case. And in this case, return the other one. And otherwise, if it's an if, then I just have to basically put it back, right? But again, so this is some, I don't know what to call it, optimized e. And this is something else. Sorry, this whole thing is the result of reducing e, right? So all of this is the optimized e. So I don't actually care about the pieces here.
And only after shorthand for saying.
So this is an at pattern, right? So I'm saying this OE now stands for this whole pattern.
Okay.
And I do want to keep this because I want to keep the optimized version, but now I'm going to put this if back, right? So if e optimized e, then something else, something. And then here I can reduce the both of the branches again.
So for the OE pattern, I guess we only get that back if it was like
Yes, so that's nowadays, right?
Yeah, I mean, as it happens, if you think about it, it's never actually going to return this if in this case.
Yeah, okay.
But if we added a few more features, like some variables or something like that,
Yeah.
to the language.
Yeah.
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 But it's not obvious that, I mean, you really have to think a little bit to see that this is impossible, right? So, so I can't leave it out, then I would complain. It's a pattern missing.
Is that actually more efficient? Is it not doing exactly the same thing that was happening already?
What do you mean?
Because I mean, what you're doing is with statement, you're just doing if the bit was true, then reduce.
Yeah.
Else the bit is false, then.
We've replaced E by a more efficient version of E, but we haven't done anything else clever.
Here, you mean?
So that's still just running if then else. Like you'd still just be running that either way. If you did.
Right, but this if then else is the final result of the if then else, right? It could have been some other if false, then this if then else, if true, then that if then else, etc. So
I mean, so okay, the situation is
It's not really optimized, more just expand it, right?
well, okay, so yeah, so all of this assumes we have variables or something so that we can actually get stuck in an if then else, right? But if we did, then it could have been a lot of if true, if true, if true, and then finally an if variable. And then this reduction here will reduce all of these if trues on the outside, right?
Yeah. Now there is a there's a classic way to get in at fight with the termination checker, because you can also regroup. Because we're doing an if on the result of an if. So we could regroup and make the inner condition. We can move this condition outward, but then we get in an interesting fight with the termination checker if we're not careful.
Yeah. Okay. So that's
Just
not.
to completely clarify, the reduce if you're running it earlier, and that makes the output more efficient.
I'm optimizing the E. Yeah.
So if you ran eval, it was eval, right? T-val on the first expression. You're saying if you run reduce if and then run t-val will be more efficient the second time.
Yes, I'm saying that the expression I get out of reduce if could be a smaller expression than the original expression.
Right now you're
because you see here in this case,
evaluating all the possible ifs is what you're saying.
yes,
Okay, got it.
I'm doing it before I run it if you want.
That's what I was
Yeah.
thinking if you do both, yeah.
So for example, now if we had an if up here somewhere, right? Type expression 3 is an if. The expression is this big thing, and if I run reduce if on it, then I just get the num2 out, right? So it seems to work. Okay, good enough. But we can actually prove that it works, right? And what do I mean by this? Like I said, I can prove that for all types T and for all expressions E of type T, if I evaluate E, then I get the same thing as if I evaluate reduce if of E. Maybe, I mean, equality is symmetric, but I think actually I like it better if I write it this way around, because it's kind of explaining what happens if you evaluate reduce if. Okay, so we could hope to prove this.
This is an a priori saying that it's more efficient to say that's the same thing when you do reduce.
It's saying it's correct in the sense that we didn't change the meaning of the program, right? You're right, it makes no guarantees that this is actually smaller. I mean, you could define the size of a program and then you could prove that the size of reduce if is
we could also write
less than or equal to
step counting version of the evaluator and prove that the number of steps is at most.
Okay, so I do this just like anything else by pattern matching on the thing. So I said it was a proof, but I'm really just writing a program, right? Okay, and then I see what I have to do. And I see in the num case, I have a reassuringly easy goal because we just said that reduces that nothing here, right? So this is just raffle. In the bit case, the same thing. And then here in the plus case, I actually have to do something. But I see, so I can do this in a few different ways. I see that it's basically the same thing, right? Except that we have to do recursive calls on E and E prime. So probably the easiest way to do this is to just rewrite by the correctness on E and the correctness on E prime. Okay, and then this is the only interesting case in some sense, right? Because this is where we actually did something. So we look at the goal and we see that this left-hand side here is stuck because it's done a with on this expression, right? So we play the usual game, why is it stuck? Well, it's stuck because of this. So we have to look at this as well, right? Oh.
Right, and something marvelous happens.
Okay,
Right.
so now it's stuck because of QQ.
Have we seen this happen with before? Because this is the superpower of width. Right. In the past, we've shown you using width to bring the value of an expression of interest to the left-hand side where we can inspect it. So add an extra column of from the result of a thing, so you can pattern match on it. But something else just happened. This expression occurred in the goal that we were trying to prove, and now in the goal, it's been replaced by the variable that we're ready to pattern match on. So width is actually doing something rather cunning. It doesn't just give you access to the value of the expression that you care about. It does maximum damage. It gives you as much leverage as possible on the goal that you can get by looking at the value of that expression.
It's not just doing a case, right? It's doing a
So it's doing
clever case.
way more than case analysis in Haskell. It's actually really giving you lots of leverage.
Right. Okay. So I pattern matched on this, and I get something very similar to before. So I'm going to pattern match again. And then we see that what has happened here is that the left-hand side, which was this reduce if, has just ironically reduced to just this, right? Okay. So then we would like to see, okay, so why is this goal true? So we would really like this thing to become false, right? Because then these two things will be solved by a recursive call. So that's kind of the thing we're trying to do, but backwards, right? So I think if we do a rewrite of reduce if correct E, then that's not going to do anything, I think.
Nope.
Because that's replacing all of these things with the right-hand side. But if I do the sim of that,
then you will be sad.
right. Okay, so what should I do here, Connor?
You should add an extra column. You should use even more if voodoo, and you should be fine not to even sim it, I think.
Yes, right.
So
this is a bit hard to get used to at first, right? I shouldn't call it QQ, I guess.
Right. So you will notice that, so the point is here that in the type of reduce if correct E, we have another occurrence of reduce if E. And with, notices that, it says this is of interest. I want to abstract this from every place I can find it. And it can find it in the type of this thing.
So that means now down here, we've actually replaced it with false in this case, right?
Yeah,
And
so we've
that's-
actually held on to the information that that reduce if E. The trouble was that we didn't remember the equation.
Yeah.
But now we've.
So it's a little bit of a pattern, I guess, that often you find yourself, you have forgotten some equation that you know that it should be true, and then what you do is you go back up to the if and you do it there rather than before you've forgotten it. So now I can pattern match on.
I don't think you can.
But
But you can rewrite.
can
some of
rewrite.
it.
Yes. Right.
And
Right, so I couldn't pattern match on it because this is not saying variable equals expression or expression equals variable, right? It's just saying expression equals expression. I can't replace all uses of false with this, or I can't replace all uses of this with false because I don't know if this is injective or anything like this, right? But I can rewrite by it, and that makes it reduce in the goal. And then here I am now done with another recursive call. Right on EF. Right. And this one's going to be the same. Okay, and this annoyingly is the annoying one, and we're running out of time. So this looks really complicated, right?
Where is Q2T and Q2F? We're not going to be them.
you might even have been able to get away with shrinking on the left. Yep, looks good to me. And
Yeah,
then,
right.
and then you've got your induction hypothesis and you're home.
And now I can just rewrite by both induction hypothesis. Yeah. Oh, I'm already rewriting this. ET and the F. Right. So it's takes some getting used to, but the main move is exactly this, to put an extra thing up together with the first if so that you get access to the equation.
I mean, the way you don't think of ideas like this all at once.
No.
You know, we realized that reduce if E was interesting. And then when we realized that once we want to deploy reduce if correct E, we've got something which mentions our reduce if E that only shows up as part of the problem after we've done the with. And that's too late. The with is, the with isn't going to abstract it from where it's showing up unless it's already present. So that's when we figure out we need to move it to where it's going to be hit by the with.
Yeah. So I choose this example partly because it's fun to do an optimization and prove it correct, and also partly because I think it's good to see that this is a bit tricky. But of course, you're not going to learn it by seeing us doing tricky things. You're just going to learn it by doing it yourself, right? So there's plenty of this in the coursework.
Can I confirm on the last line? The first bar is part of the width, the second bar is part of the width, the third, fourth bar are the rewrites.
Yeah, so here I'm starting a new rewrite. Yeah.
Okay, so that's so in this, the third and fourth bar are sort of 4 bars.
They're all
All of these problems.
yeah, it's a rewrite by this, rewrite by this, and rewrite by this.
Yeah,
Right?
but then the first,
These are just separating the two widths.
yeah, okay.